Good day, everybody. Justin Miller, Oxnard College Physics. We're going to be looking at some ray diagrams for spherical mirrors today. And let's just get started. So we've gone over all the math behind spherical mirrors. So let's just get to actually producing proper array diagrams. So got proper ray diagrams for spherical mirrors. Three primary rays. Three primary rays are used. So we want to look at those rays and understand their behavior and consequently utilize them to produce our ray diagrams, a depiction of where the image is formed due to interaction of an object and a spherical mirror. So let us just go through this. I'm doing some colors, so when we go ahead and do some ray diagrams, you can see. So we'll do number one. First ray is going to go parallel to the principal axis and reflect such that it goes through or is aligned with the focal point of the mirror. So it goes from the tip of the object arrow travels parallel to the principal axis. And then it reflects off the mirror. Such that it goes through or is aligned with the focal point. All right, so there is our first ray. Second ray, pretty easy. It's actually the easiest one to deal with. And it is a ray that goes through or is aligned with the goes through or is aligned with the center of curvature and just reflects back upon itself. Because if it goes through or is aligned with the center of curvature of the mirror, it will strike the mirror at normal incidence and just reflect back upon its original path. So, number two. Ray goes from the tip, the object arrow, and travels such that it goes through or is aligned with the center of curvature, such that. Stop me. Center of curvature. And then reflects. Back upon its path. Back upon its incident path. All right, that leaves us with one more. See if we can squeeze this one in here. A nice different color. How about we use some red? Sounds good. All right, number three. Number three is somewhat like number one in reverse. This one is going to go through or be aligned with the focal point and then reflect off the mirror such that it travels parallel to the principal axis. Things are reversible. So that's this one. Number three. Ray goes from the tip of the object arrow. And travels such that it goes through or is aligned with the focal point. And then reflects parallel to the principal axis. Whew, I squeeze them all in. Great, because what we want to do is just look at the utilization of these three rays. So we'll just go through them, simple ray diagram, then we'll do a couple problems that utilize the ray diagrams and some of the math behind image formation and make sure that everything correlates and kind of go from there. So let's look at a general case where we've got ourselves a concave mirror. And should we freehand this? That always gets a little ugly, but sometimes it's uglier to actually try to draw it out. We'll just draw it out there, why not? So we're going to take ourselves a concave spherical mirror. We'll go ahead and draw in. Yeah, this has to be semi-free. That's okay. Draw on the principal axis here. Actually, let me draw in the mirror itself. Kind of get a sense of where the center is from this sector here. We'll just say the center is about right there. Get rid of this extraneous dot, dot, dot. This is going to be our concave mirror here. We'll draw ourselves in a principal axis. The principal axis goes through the center of curvature and goes through the mirror at normal incidence. And we note that for spherical mirrors that the focal point is halfway in between the center of curvature and the mirror along the principal axis. So that looks like about 23, so say like 11.5, that sounds good. Let's put the focal point like right there. So we got ourselves a focal point, got ourselves a center of curvature. All we need left is an object. So we'll throw in an object arrow here. I'll put the object down here, why not? So there's our object. And what we just want to utilize is these three rays and see how the image formation takes place regarding, well, using them. All right, so let us just do this. We've got ourselves ray number one. Ray number one travels, everything's from the tip of the object arrow, travels parallel to the principal axis, and then reflects such that it is aligned with or goes through the focal point. If it is a concave mirror, it will go through the focal point. If it's convex, well, light can't exist on the other side, so that's when the aligned with comes into play. We'll take a look at that a little bit later. Nonetheless, let's just take this one here, put ourselves do the best I can here on the chalkboard, whiteboard, excuse me. That's always a problem, for me at least. That looks okay. It's a little messy spot. It's okay. We got ourselves this incident ray strikes the mirror, and then this ray will be aligned with this focal point and actually go through it. Ray continues onward. All right. And then we've got ourselves the second ray. Focal point back in there. Second ray. Well, the second ray says it goes from the tip of the object arrow through the center of curvature, or is aligned with. In this case, it physically goes through it, and then just reflects back upon itself. That is our purple ray here. So we'll look at this. This ray is going to go something like this. So, tip of the object. Ooh, going to strike the mirror. And again, since it goes through the center of curvature, it's striking the mirror here at normal incidence. So we've got incoming, and then well, it's just reflected. It keeps on going. That's fine. I'm not going to draw an extension of it. Not really necessary. What do we see already? We see that these two reflected rays are physically intersecting right there. That's where we should have the image of the tip of this object. But even though we got two, we always do three with proper ray diagrams to make sure that we haven't messed something up. Because as you'll see, some of these ray diagrams get a little bit tricky. The third one's kind of like a check to make sure that, yeah, you did this right. So let's just go ahead and do the third. Always do three, especially on exams. Excuse me. Oof. So, third ray goes from the tip of the object to arrow and travels such that it goes through where it's aligned with the focal point, and then it reflects parallel to the principal axis. So this ray is going to go something like this. That looks decent. I can hold this in place. Through it, strikes there, and then what does it do? It reflects off parallel to the principal axis. So you get this parallel. And this isn't going to be perfect, but it's pretty close actually. That's really good. That looks about parallel there, semi at least. Ray continues going that way. Here's the incoming, the outgoing. What happens? It intersects at the same spot that the other two do. And ultimately, any rays that are reflecting off of this will intersect at this point within certain conditions, small angles with respect to the principal axis. But we're not really worried about that in this case. We're worried more about the actual image formation and utilizing these ray diagrams. So there's where the tip of this object is. There is the image. So it's like light is emerging from the tip of this image here. And that really plays down all the way translated to the principal axis for every part of the object itself. So it looks like light's physically coming from there, and actually it is. And that's why we identified this as the image, because it looks like light's coming from there. Light is coming from there, emanating just like it is from the object, diverging outward. So ultimately, this is how we utilize ray diagrams, and the best thing to do is when you have problems involving spherical mirrors, you math it out and you make sure that your math agrees with the ray diagram that you produce. If one's wrong, they're not in agreement ultimately, you've done something wrong. So the ray diagrams are nice to look at because it gives you a good physical representation of the image formation itself, but it's always a good check for the mathematical correlation of the problem. So at that, let's look at a couple problems that involve this and see the different incorporations of ray diagrams depending on what type of mirror we have and where the object is located relative to the mirror. Shall we? We shall. Be right back. All right, so here we go. Here's the problem. Let us look at this. We've got ourselves a spherical mirror that is concave. It has a radius of curvature that is 20 centimeters, and we want to look at where is the image formed, what is Q ultimately. We want to know the magnification, we want to know the orientation, and we want to know the image type, real or virtual. And we want to do it for three different cases, where we have an object 40 centimeters from the mirror, 15 centimeters from the mirror, and 5 centimeters from the mirror. And we also want to produce proper ray diagrams for each of those three cases. So let us just go ahead and do this, shall we? Let us math this out really quick, because the math's pretty straightforward as we've seen. We've got ourselves, in general, that for spherical mirrors, we've got that 1 over P plus 1 over Q is equal to 1 over F, and that F is equal to R over 2. So we could go ahead and throw what F is over here. We've got F has to be equal to 10 centimeters then, because the radius of curvature is 20. So there we go. And what can we do with this then? Well, we can just go ahead and solve this for Q. So this solves out for Q. We'll put the 1 over P on the other side, and then we'll take the inverse of both sides to get Q. Q is going to be equal to the quantity of 1 over F minus 1 over P to the negative 1. And at that, we can go ahead and start solving this out for, we'll just do part A first. So for part A, P is equal to 40 centimeters. We've got that Q is going to be equal to 1 over 10 centimeters minus 1 over 40 centimeters to the negative 1. Let's just go ahead and put that in a nice calculator here. 1 divided by 10 minus 1 divided by 40. Just a negative 1. 13.333. 13.333 centimeters. So that's where the image is located, 13.333 centimeters from the mirror. Came out to be positive. Sign convention says that for mirrors, that is going to be on the front side of the mirror. That's good. Let's look at some other things. We also want to know what the magnification is. Well, the magnification is equivalent to negative Q over P, which will then be negative 13.333 divided by P, which is 40. We'll drop the centimeters because they cancel each other out, and we've just got ourselves that this is negative 0.333. Negative 0.333. So there's the magnification, lateral magnification. Notice the magnification came out to be negative. M equaled a negative value. This says inverted image. It also says, because the absolute value of M is less than 1, that the image is smaller than the object. 0.333 times the object height. So those are two nice things that we could definitely see. And we've also got, because Q is equal to positive, we have to have the physical intersection of light rays, because it exists on the front side of the mirror where light physically exists. So this correlates with a real image. Physical intersection of light rays. So there we go. We've got ourselves the math behind this all and the quantities. Now it'd be a nice time to just go ahead and look at a ray diagram for this. Shall we then, and make sure that what we found mathematically correlates with what we expect to find in the system. So let's do this. I'm going to go ahead and this gets a little tricky. This will be scaled to some degree, not specifically to those values. There's a circle, kind of a circle. I'm going to go halfway in between. There's our center of curvature. So that's how I kind of get the center for these. Getting too crazy. We'll just go ahead and draw ourselves a principal axis in here. And let's do this. Center of curvature, there's the principal axis. This is 56. So we want to go 28 approximately. So there's our focal point, halfway in between. And then if we double this, we are 40 centimeters away. So 56, 56, and 12. So we go another 12 centimeters on top of this. I will elongate this a little bit. I'm trying to scale this out nicely. Put our object right there. So here's our center of curvature. Here is our focal point there. This is 10 centimeters, this is 20 centimeters, and this is then 40 centimeters, within reason. So, let us do our ray diagram, shall we? All right, we shall. First ray, parallel to the principal axis, reflects through the focal point. I know it's going to go through because this is a concave system, and I'm going to try to do this the best that I can with instruments that I have. Parallel to the principal axis, kind of. And then goes ahead and reflects through this focal point. Great, there's our ray number 1. Ray number 2 goes through the center of curvature, then reflects back upon itself. See if we can do that. Center of curvature, tippy top. There we go. That looks okay. Just have to do it. So it continues going on. Something like this. And then it just reflects back upon itself, so we're all good with that. We see that they're intersecting right there. That's great. Hopefully the last one intersects there too. Let's see, we'll use red for that one. Stay in character here. And, all right. This one's gonna be a little bit more difficult for me, but I'm used to it. Used to it. It's a little bit too high, but let's kind of drop it down a little bit there. Strikes there, and then goes parallel to the principal axis. It should be down a little bit more, so it should be down like more like this, but that's okay. Within reason, we're getting a decent ray diagram here. So, what do we get? That's right, they all intersect right there, within reason, and we've got ourselves our image. What do we notice about the image in this ray diagram? Well, first off, is that really about 13.3 centimeters away from the mirror? Well, here's 10 from here to the focal point. There's 10, this would be 20, 15 would be directly in between those two, and that being 13, that looks decent, decent. So that seems to be in agreement. It's inverted. We got a negative M inversion. Hey, that correlates. Good, it's smaller in size. Is that about 1/3 of the size? I don't know, maybe within reason, yeah. And we have a physical intersection of light rays. It's got to be a real image then. So this depiction here definitely agrees with the mathematics that we utilize to solve it out. So we check it off. Good job. We move on to the next. All right, let us erase this. Got it? Good, all right. This isn't gonna change here. What's gonna change is this stuff over here. Changing where P is, where the object is, excuse me, what P is. And we do just that. All right, so now we want to go to part B, look at an object distance of 15 centimeters. So B, we're just going to go ahead and put 15 in for that, and we've got ourselves that Q will be equal to 1 divided by 10 centimeters minus 1 divided by 15 centimeters to the -1. Let's calculate that out. Oh, we get ourselves 30 centimeters. So now we've got the image is 30 centimeters away from the mirror, and the object is only 15 centimeters away from the mirror. That's interesting. Image is further away. Let's go ahead and look at what M is. M again, negative Q over P. That is going to be negative 30 divided by 15 in this case. Centimeters cancel out, didn't really need them there. We get ourselves a -2. Well, this tells us two things. The negative sign says this is inverted. an inverted image. The 2 says that the image is twice the extent of the object, 2 times as large. And that's what we've got with this. We've got Q is positive, M is negative, Q equals plus. We've still got ourselves a real image. M is equal to a negative, inverted. And there we go. So let us do a ray diagram for this one, shall we? All right, I start to have to make things a lot bigger, so I'm going to kind of freehand this a little bit to a greater extent. Let's see. So, freehanding them out, often run into a little disagreement in some cases with where the 3 intersect. One may be slightly off from the others. That's going to be okay. Freehand graph paper come out better, but you have to be careful of a little bit of things, and usually that has to do with how large you make the object to begin with. You really want to utilize small angles, or you start to get these distortions, spherical aberrations, if you will. Nonetheless, you can still go ahead and do this stuff. Put this here so we can kind of count this out. Let's that way to do it. That's okay. So let's go like this. Get ourselves a principal axis. Keeps on a trucking, and we've got ourselves that to that. Well, again, it's about 23. 11 and a half again. So that's our same old mirror there. Nothing's changed. We've got our center of curvature. We've got our focal point there. What has changed is where we're putting our object. Now the object is directly in between the focal point and the center of curvature. That's 10 centimeters away. That's 20 centimeters away. Directly in between, we'll do as directly as possible. That looks about good. So I'm just going to make a little object in this particular case, as you'll see why here momentarily, again, because we want to keep small angles. So let's just do this. First ray, pretty easy. It goes parallel to the principal axis, and it will reflect through the focal point. So we can do that. Parallel to the principal axis. Trying to, and then reflects through the focal point. Just keeps on going. So it's kind of stationed up here. All right, we'll take it. So then we've got that one. And then we've got the next one, goes through or is aligned with the center of curvature and reflects back upon itself. This one's a little bit more tricky because it can't go through the center of curvature and hit the mirror. So this is where aligned with comes into place. So this one lines up with the center of curvature. Again, if it's lined up with the center of curvature, it still strikes the mirror at normal incidence, and thus will reflect back upon its original path. And something about like this. So this is going to go like this. You come back and keep on going. These two need to be extended off, as you can see, because they're not intersected yet, but we're getting close. And the last one. Let's look at this last one. We've got ourselves, it goes through or is aligned with the focal point and reflects parallel to the principal axis. It can actually go through it, so we'll just take it going through. And the tip. There. Looks decent. Comes on down. It's down here, and then goes parallel to the principal axis. A little hard for me to see, but it's okay. And it's off a little bit, because I made that a little bit too big. Things are too condensed. But within reason, these are all intersecting around the same spot. You kind of elongate this one outward, elongate this one outward. You got everything is intersecting somewhere right around in here. So even though it's a little bit blurry, that's okay. We'll just put this here and say, there's our image. What we get, however, is a good representation of what the mathematics said before. It said that the image would be 30 centimeters away from the mirror. Well, this is 10, that's 20. Hey, that looks like about 30, huh? 10, 20, 30, that's good. Check that off, it's inverted. That's good for the magnification. Is it about 2 times the size of this? Well, 2 times the size. That looks fairly close. So all in all, we've got something that does correlate. If it's not perfectly drawn, it still does give us a good representation. Check. But notice how we had to utilize the second ray aligned with the focal point. And that's going to be something that you've got to be really careful of. All right, let's look at this last case. So the last case is with an object distance of 5 centimeters. P is equal to 5 centimeters. So what do we get out of this? We've got ourselves, this is part C, Q is equal to 1 over 10 minus 1 over 5 centimeters to the negative 1. Let's just see what that is. 1 divided by 10 minus 1 divided by 5 to the y is negative 1 gives me, excuse me. Just clear this out. I should just put the answer, but I didn't calculate it. 1 divided by 10 minus 1 divided by 5. That's right. It's a negative 10. Negative. We'll come back to that. Let's look at the magnification. The magnification being equal to negative Q over P is going to be negative 10 divided by, well, P is equal to, what is it equal to? P is equal to 5, right? 5. All right. This is going to end up being equal to 10 divided by 5. The negative signs cancel out, and that gives us a 2. So what do we get with this? We have the Q's negative. That means that the image is on the back side of the mirror. Light can't physically exist on the back side of the mirror after the interaction. So what happens? This has to be a virtual image. The magnification is positive. What does that mean? Upright image. So we've got an upright image that's virtual, that is 2 times the height of the object. Let's see if we can produce this. These ones start getting a little bit messy because everything is so squished together. So let me see if I can make this a little bit bigger than usual. Run into big giant problems. Usually they're a little problematic to begin with. That's okay. Oh. All right, so we'll draw in our principal axis here. You can already see this is a little bit off. Okay. Draw that in, and let's just put this about halfway in between. So we've got ourselves a C, we've got ourselves an F, and then we're going to put our object halfway in between the focal point, which is 10 centimeters away in the mirror. So we've got ourselves a little object right there, making it very small for a reason here. to be helping me out in producing this ray diagram. Excuse me. And we just go through the motions again. First ray goes parallel to the principal axis and reflects through the focal point. So parallel to the principal axis, that's easy enough. There it goes, parallel to the principal axis, and then it reflects through the focal point. Hey, that's easy enough as well. There's the focal point right there, lined up with it, and there's a little darker. That's what I was looking for. There we go. This ray just keeps on going onward that way. Second ray. Well, the second ray goes through or is aligned with the center of curvature. Switched colors, that's my bad. Center of curvature is right here. There's the tip of the arrow. This one has to be aligned with. So aligned with is kind of like this. So it's going to go whoop, and then it's going to continue on that way. And what you should notice is these two rays are divergent from one another. The further away they go, the greater the spatial separation between them. So they're never going to intersect. That's telling us something that we're not going to get a real image. Let's look at this last one, and then we'll deal with the actual image here. Last one, hey, it is aligned with or goes through the focal point and then reflects parallel to the principal axis. This one has to be aligned with. Can't go through it and strike the mirror, so we line it up with the focal point. About like so. The focal point right here. So it's aligned up with it. It comes and strikes the mirror there. Whoa, whoa. And then reflects parallel to the principal axis. So let's try to do that. Within reason, I'm good with this. So we've got these three rays on this side. These are all divergent, never to intersect, which means that we have to, excuse me, which means that we have to look at how they trace back to a point of intersection, where it seems like light's emanating from, even though it's physically not doing so. So now trace back the reflected paths. To find the image. All right, so I'm going to trace them back with their original colors here. So I'm going to do it in reverse. We've got ourselves this last one. The reflected path is that one right there. So I'm going to trace that reflected path back onto the other side and just kind of extend it that way. So that is the reflected path of that last one traced back. Let's look at the reflected path of the second one, sort of traced back here. Give ourselves the reflected path is along this right here. So this one sort of traces back like that. You can see that those two are intersecting right there. That's nice. Let's see if that third one intersects there as well. Well, the trace back path of this one, remember this one went parallel to the principal axis. See, I just did that one. That was the first one because I changed colors. That was the first one. The second one was this center of curvature one. That one's already aligned along its path. So I'm just got to line this on up. So it's lined up with the center of curvature. Extend it out. What do we get? Those three rays all intersect about right there. And there is our image. What do we get with that? Well, let's look at the distance. We were told that the image would be -10 centimeters from the mirror, the negative being on the back side. Well, that's 10 centimeters on the front side, the distance to the focal point. That looks like about 10 centimeters on the back side. That's a check. It's virtual because the light isn't physically existing here. It just looks like light's coming from there, but that's still identifying a virtual image. It's upright, just like the magnification said it would be, and it's enlarged in size, approximately, in this case, twice the size of the object. So these are the three different types of ray diagrams that you generally run into with concave mirrors. What we'll look at next is ray diagrams with a convex mirror. Those ones you gotta be a little bit careful of too, but nonetheless, this is what we want to do. So be right back and we'll look at a convex case. Do a nice little problem. All right, be right back. All right, so let's look at a problem involving a convex mirror, shall we? Here's the problem. Okay, so we've got ourselves a convex mirror. We're told where the object is placed, object distance of 30 centimeters from the mirror, and we're just given the magnification being positive 0.75. So let's just go through the questions and answer them up. We want to know where's the image located. We want to know what is the focal length, what is the radius of curvature, what is the image height. Given that the object height is 4 centimeters, we're going to produce a ray diagram. So that all sounds pretty nifty, does it not? So we've got a couple expressions that we utilize for spherical mirrors, right? We've got the 1 over P plus 1 over Q is equal to 1 over F. That's good. And we've also got the M is equal to negative Q over P. Those are our two primary expressions that we have for spherical mirrors. So we want to figure out what Q is, right? So this one's not going to be that helpful because we don't know what the focal length is. That's actually asked in part B. So let's see if we can use this, right? So yeah, of course we can. We know what M is equal to, 0.75, and we know what P is equal to, 30. So what do we have with this? Well, M is going to be equal then to negative Q over 30 centimeters, which is equal to 0.75 centimeters. So we can get what Q is pretty easy, right? Q is then equal to negative 0.7 centimeters, 0.75 times 30 centimeters. So what do we do with that? 0.75 times 30 gives us 22.5 with the negative sign out in front. Negative 22.5 centimeters. So there's Q, image distance, excuse me, came out to be negative. It's on the back side of the mirror, which also means that it has to be a virtual image. So we've got a couple things going for us. We know it's virtual, that we're going to have to trace back rays on the back side when we're doing the ray diagram, and we've got that. So then we're off to figure out what the focal length is. The focal length we can just get from that first expression there. We've got B, we'll just invert it, right? And we can write that F is equal to the quantity of 1 over P plus 1 over Q to the negative 1, which then gives us 1 over 30 plus 1 over negative 22.5 to the negative 1, which gives us F is going to be equal to 30 minus 22.5. Negative 1 gives us negative 90. Negative 90 centimeters. Pretty big focal length. Notice it came out to be negative. Negative is telling us this is a convex mirror. So that's something that we already knew, but we get a reiteration. Excuse me, oh my gosh. We get a reiteration of that. All right, we can move on to a part C. C is just asking us what is the radius of curvature? Well, the radius of curvature is equal to 2 times the focal length. 2F, which is then going to be equal to a negative 180 centimeters. Wow, that was pretty easy to figure out. And then we're left with an H prime. Well, how are we going to figure out what the image height is? We have to look at the magnification. Note, the magnification is defined as H prime over H. So we get that H prime, the image height, is equal to, say, H, the object height, times the magnification. So if we're told that the object height is 4 centimeters, this is going to be equal to then 4 centimeters multiplied by 0.75. What is 3/4 of 4? That's right, it is a 3. Came out to be positive. We've got an upright image, and there we go. It's a little diminished in size, 3/4 the size of the object. So that leaves us with part E, doing the ray diagrams. It's going to be, again, a little bit careful with dimensionalizing things here. We've got a really big radius of curvature and a really big focal length, and the object distance isn't really that big. So I'm going to have to kind of compact this a little bit, scale it way down. That's okay. We'll just do the best we can. I'll do the best I can. You always do the best you can. All right, so let's do this. So we've got some sort of circle here. Let's say that the center is about right here. Why not? So there's our center of curvature. That's going to be 180 centimeters away. It's going to be a crazy scale. That's okay. So there's our center of curvature. Take about half that distance. I'm going to kind of do this quick. 22.5. Let's see, that's the wrong side. 23, 40, 50, 65, 32, 2, somewhere right around in there. So there is focal point, center of curvature. So that's 90 centimeters. Not really half. That's decent. That's 90 centimeters, so a third of that is going to be our object distance, 30 centimeters. So that's 10, 20, 33, so we got about 11. Let's see, 10, 11. So we're putting our object right there, next to this mirror. All right, let's see how this looks. So this may not be super pretty, but an object. Don't want to make it too big, don't want to make it too small though. That makes things really difficult with this, but we make it nonetheless, and we go ahead and start producing our ray diagram. So, first ray, parallel to principal axis, and reflects such that it goes through or is aligned with the focal point. So in this particular case, we've got ourselves a convex mirror. In a convex case, we always get divergence after the reflection, but that divergence with the parallel ray will be aligned with the focal point. So we got that this particular ray is actually going to reflect off in that direction, but I already know I'm going to have to trace things back, because with convex systems we will always get virtual images for single interactions, always. So I'm just going to go ahead and trace it back. Dashed line to show the alignment and to have a trace back path. So there's that first ray. Then we've got the second ray. Well, the second ray goes through where it's aligned with the center of curvature. The center of curvature is way over here. It can't go through it. It's got to be aligned with it. So, excuse me. This particular ray is going to do something like this. Come strike this mirror, strike this mirror, and then it's going to continue out that way, but again it's aligned with the center of curvature, so I'll just go ahead and show that alignment. So this is the reflected path, incoming reflected along the same path. There's the alignment with the center of curvature, and look at, we got that these two paths trace back to a point of intersection right around here, which is where the image should be located. Fantastic. Let's do one more, because we need our third ray, make sure everything works out here, at least within reason. Well, the third ray, again, is going through or is aligned with the focal point and then reflects parallel to the principal axis. So this one is initially aligned with this focal point right there. So there it is. So what's it going to do? It's going to come down Just going to come down and hit the mirror there. It is aligned with this, but I'm not going to draw that alignment in because I only want to draw in the reflected paths for the image formation. So we know that this one's aligned with this initially, and then it's going to reflect off parallel to the principal axis. So reflect off parallel to the principal axis. That looks pretty good right there. So this one's going to go out like this, but we want, once again, to trace back this path. Here's the trace back path. What do we get? The blue, the purple, and the red all intersect about right there. There is our image. Object distance, image distance a little bit smaller. This was supposed to be 30 centimeters. This is supposed to be 22.5 centimeters on the back side. It's a little bit smaller in height. This is supposed to be 4 centimeters. That's 3 centimeters. Within reason, it matches up pretty good. Now, the problem generally with these ray diagrams for convex systems is the extent of the object in the first place. Again, we want small angles, so sometimes making the object too big distorts things, or too close to the mirror. In this case, with the focal length being so big, it's hard to expand things out too large, but nonetheless, we still get a decent representation of it. Matches mathematically what we expect, upright, diminished in size, virtual, and that's it. So there you got it. There you have it for some spherical mirrors. All right, thank you. Take care.